Okay, we're going to begin with a little bit of review from Orgo 1, which you should know already, but just to make sure some of those cobwebs get out of your head. If you recall, an SM1 reaction involves an alkyl halide, and the leaving group first takes off. So that's going to leave and produce a carbocation. Anytime you have a carbocation, that means that you can have rearrangements of this particular structure if, say, you were to have something that's more stable next door where that positive charge could reside. Remember, sp2 carbons, in that particular case, we've only got 3 bonds to that carbon. That is a flat atom, which means that the nucleophile can attack from either the top or the bottom of that plane. So if you have something that's flat, it can do that, which means that you get a racemic mixture of your product, whatever that product may be. On the other hand, an SN2 reaction is stereospecific because this happens in one fell swoop. So as the nucleophile comes in, the leaving group leaves at the same time, which means there is really only one way for that nucleophile to attack, and that's from the back. And this leaves from the front, putting the nucleophile in an inversion of symmetry, or the opposite stereospecificity than the leaving group that just left. Okay, so you can recall all of those details, go back and review that if you need to. There's solvents that take place and make a difference, but one big thing to recall is that a tertiary alkyl halide is helpful in an SM1 to occur. Primary and secondary usually go SN2, although a secondary could go technically either direction depending on the solvent and that type of thing. Okay, so when we're talking about alcohols, we have 2 major types of reactions that are the displacement types of reactions, and then we also have elimination reactions. So let's begin with the most common SN2 types because they're sort of the easiest to take care of. Actually, you should already know this one, in that you already start with alcohol, and then tosyl chloride. Basically, this is the tosyl group, when in combination with oxygen like this, as you see here, OTS, is an incredibly good leaving group. Okay, so once you take that tosyl TSCl and pyridine, which I'll show you the mechanism of in just a minute actually, this nucleophile can easily replace that OTS group with no problem whatsoever. If you want to look at the mechanism for that, I'll go ahead and skip forward here. Well, I wasn't planning on it. You simply take an alcohol such as this, and this is a butyl group over here, but this alcohol attaches to the sulfur, chlorine leaves, and then the pyridine that's used, this is pyridine, that's a base, comes and removes that hydrogen, electrons go back down, and bam. So you have an SOOO, and as you know, that means that the oxygen is pretty stable on its own, so a nucleophile can easily come in here, and this guy's pretty happy to be out by himself. And that's where you get the nucleophile, in that position. Okay. If you have a simple acid, this can actually proceed via SM1 or SN2 depending on the reaction conditions, your alkyl halide and that type of thing as we had up here. But essentially your X will end up replacing where this OH is. Here's the mechanism. First your alcohol goes in, grabs a hydrogen, electrons go back to the X, making it a negative charge. And then depending on whether or not you have an SN2 or an SM1 type of displacement, either this could happen, this can attack on the R as that leaves, or the water molecule first leaves and then the X attacks. So again, that depends on if you're going SM1 or SN2. PBr and PCl3 with pyridine, on the other hand, are actually just going to go SN2. So in this case, we have an alcohol, and we put it with PBr3 and pyridine, you'll end up with a bromine right here. If you were to use PCl3, you would end up with a chlorine right there. And here's the mechanism. The alcohol, the oxygen from the alcohol, comes and binds to the phosphorus because that sort of acts as a Lewis acid. Your bromine then leaves. And that basically leaves your oxygen bound to 3 different things, including the hydrogen that it was bound to before over here. So the base, the pyridine, as you see right there, this guy comes and grabs the hydrogen, electrons go back down, and we end up with this OPBr2. Now, this is a decent leaving group, and there's a bromine that you just let go from over here. So as long as you're not putting anything else in, the bromine says, hey, I want in there too, and this guy leaves, and that's exactly what you end up with. So in this case, if the OH is sticking towards you, the bromine should be going towards the back. Just a minute on this base. Pyridine is stinky, stinky, stinky. But it is a very good, easy base. It's not going to be an incredibly strong base because obviously you're going to end up with nitrogen with a positive charge there. But it's not really reactive with much else, so we like to use that as a base, especially with alcohols. Okay. Now, suckle. Sockatool is what I always say with this. But the sockle, or SOCl2 with pyridine, is going to do something very similar to what we just saw, and actually it would do the same thing as PCl3, although there's advantages and disadvantages to each, which I won't really go into. But this OH right here is again replaced by chlorine, and it's in an inversion of configuration because you have an SN2 type of mechanism that's occurring here. And note that this is very similar to what we just saw with the PBr3. The electrons from the oxygen go over to the sulfur, chlorine leaves. You end up with a positive charge on the oxygen. Pyridine then comes and removes that hydrogen, electrons go back down. And now you've just made a good leaving group. Chlorine that you just released from over here comes in and attacks, while the O2SCl leaves, and you end up with a Cl right there. Okay, so as I was saying, the tosyl chloride, you can again end up doing this very similar type of reaction. So see, these two are very, very similar. Your tosyl chloride is technically a better leaving group, simply because you have more stability for that negative charge on the oxygen, given that you've got 2 oxygens to resonate that with instead of just 1. But this nucleophile will easily replace that, and that's what you end up with as a product in this case. If, however, you were to add a stronger base, you could actually end up with an elimination product. And that could go via E2, hopefully, where the base would come in and abstract a hydrogen that's next door. Electrons go down and this leaves. So if you recall, it wasn't just SM1, SM2 that we dealt with last semester. It was SM1, SM2, E1, E2. We always preferred using an E2 type of elimination, and there's a reason for that, which I want to talk about here in a second. But we still kind of like that better. At least I do. Unless it doesn't matter. And yes, you're most of the time going to end up with a transalkene. You could kind of force that if you really needed to in certain cases, but it would be pretty rare. Okay, so that leads us into really looking at elimination types of reactions with our alcohols. And these are certainly possible because when you can have a substitution reaction, remember elimination reactions are constantly battling with your SM1, SM2 to see which one can actually take over. And surprisingly, we could actually do an elimination with strong acid. So strong acid and heat is probably one of the most commonly used forms of elimination, but it is kind of reversible, so you have to be watch out for that. I didn't draw that in, but it is reversible here. So in this case, you have an alcohol. It comes and grabs a hydrogen from the sulfuric acid, and electrons go back down. And now you basically have a water molecule that's ready to leave. In order to get that off and to drive this equilibrium in this direction, right, because you're taking a water molecule and you're making it leave at this point, A lot of times what we do to help drive that reaction is we distill the water off. So you're going to heat it up, hopefully your water comes out, and I know I drew a water molecule right here, but anything that's in the solution that can act as a base could then come and remove that hydrogen, electrons go down, and you end up with your elimination product. Now that's obviously an E1 type of elimination, which means that you're making a carbocation. Whenever you have a carbocation, you can have a rearrangement happen. So be careful with those because you can always have that rearrangement happen. And that's part of the problem with it, is if you really want one thing to happen and it's not what you, it's not that you wanted to get the most substituted elimination product, then this really isn't the route to go. So if you have more than one alkene that's possible, the most substituted was going to end up being your majority product. And let's say it wasn't even the thing that you got as your E1 product. Here's what ends up happening, is that there's, let me just take you from the beginning to the end here. You could end up with having a primary alcohol where you ended up with a alkene on the end, but due to the fact that you are constantly in equilibrium, this guy can actually move so that you end up with your alkene in that position. And yes, a vast majority of those will definitely be trans in nature. Here's how that works. So again, you start with the OH coming in and grabbing a hydrogen. Electrons obviously go back to that oxygen there. A base could come in and abstract that hydrogen, electrons go back, that falls out. This would be if you have an E2 type of elimination. So you could get this alkene bond, but then a hydrogen could actually come through and electrons donate over to that hydrogen, and you end up getting this type of structure, where the base could come back and take that hydrogen instead, giving you the alkene at the most substituted position. And it's not what you expect, so you have to be careful with those. Those can be really cantankerous. That's exactly why we like our little superhero that I refer to as Paco to come to the rescue. Because this guy goes E2, there's no rearrangements. He will still prefer E over Z, but you can basically count on this one to do what it's supposed to do. So simply, if you have like a secondary alcohol in this particular case, with Paco, 0 degrees in pyridine, you end up with your double bond right there. It doesn't migrate, so like say if you were to have an R group right here, it's not going to start migrating over, which you would have if you were in acidic conditions. Okay, so the alcohol, this looks very similar to PCl3, doesn't it? But the difference is the POCl3, this will help you remember. The double bond to oxygen here gives you a double bond in the end. If that helps you remember, go for it. But the OH comes in, donates electrons to the phosphorus, the chlorine leaves. Again, you would have some pyridine come in and abstract that hydrogen, and it moves out onto that oxygen because otherwise it's a positively charged oxygen. And then you have a lot of extra pyridine in this particular reaction. You purposely want to drive it by having extra pyridine in this reaction because it's required as a base to come and abstract a hydrogen that's next to that POCl3, that leaves, and you end up with your Zaitsev elimination right there. Okay, thank you very much.